Chapter 4, Atoms and Covalent Bonds. In the last chapter, we looked at ionic compounds. So let's compare ionic and covalent. Generally speaking, when we look at state of matter, which is solids, liquids, or gases, ionic compounds are almost always solid at room temperature. On the other hand, covalent compounds tend to be gases or liquids, although there are quite a few that are solids. Melting point. So the temperature with which we go from a liquid to a solid, or solid to a liquid, means the same thing. Melting points, also boiling points, right? When we can go from a liquid to a gas. Melting points and boiling points of ionic compounds are much, much higher than similarly massed covalent compounds. So we only can really compare things that have a similar molecular weight. Melting points and boiling points are always higher in ionic compounds. And why is that? Because the energy and the bonds of ionic compounds are much higher. So that electrostatic force that holds the ions together in that crystal lattice structure are higher in energy than what we see in covalent compounds, where we're just sharing electrons. So covalent bonding. Why would two atoms share electrons? Here we have two fluorine atoms. These dots here represent the number of valence electrons. Valence electrons are the electrons in the outermost shell. So fluorine, recall, has a 2s2, 2p5. So they have a similar desire for electrons. So instead of there being a transfer of electrons from one fluorine atom to another, they share one of their electrons. And the guiding rule is still the Octet rule, which says we want to become like a noble gas. So for fluorine, that means having 8 electrons in its outermost shell. So this is what we call a Lewis structure, which we'll go over how we do those. A single line between two atoms represents one shared pair of electrons. The remaining electrons that are surrounding fluorine here are what we call lone pairs of electrons. So we simply just call this a single covalent bond, right? If we have a double bond, then we have twice the number of electrons. If we have a triple bond, then we have triple the number of electrons there. But always one bond is going to represent one shared pair of electrons. So one electron comes from this fluorine atom, one comes from this fluorine atom. We share so that we have 8. So this is looking at a potential energy diagram of when two hydrogen atoms come together. And we notice that here we reach a minimum energy, which is driving force for most chemical reactions, is that we're trying to have the lowest amount of energy because it's the most stable. So as our hydrogen atoms are approaching each other, we see that we can reach this minimum. This is the comfortable place for which these two atoms can exist next to each other. If they start to get closer, we see that the potential energy goes up because now we're going to see a much higher repulsive force between the two nuclei. So we have to keep in mind, right? Electrons are negative, protons are positive. So one atom's nucleus can attract an electron from a neighboring atom. So how do we represent compounds? Well, first of all, we have a chemical formula, and any chemical formula is going to give you the number and the type of elements that are present. So we have, for example, down here, 1 nitrogen atom, 3 hydrogen atoms. This is a chemical formula, 1 carbon, 4 chlorine atoms for this compound. So molecular formulas are representing covalent compounds. So notice we don't see any metals that are showing up. Covalent compounds do not have metals in them. That's strictly for ionic compounds. And the only exception to that rule is when we have the ammonium ion, which is that NH4+. So molecular formula represents a discrete unit of atoms that are only bonded to each other. In ionic compounds, we have what we could call a unit formula, which, remember, there's just a repeating set of positive ions and negative ions, and that's how that crystal lattice is formed. A structural formula is going to take a molecular formula and show the connectivity between those atoms. So we can actually see what the structure is of a particular compound. How are the atoms connected to each other? Is this nitrogen connected to a hydrogen, which is connected to another hydrogen and another hydrogen? Are they all in a row? Or are these three hydrogen atoms coming off just the nitrogen atom? So structural formulas tell us how things are connecting, how our atoms are connected. An empirical formula gives us the smallest number whole ratio of atoms in a compound. So this here is hydrazine. Notice we have N2H4. We can simplify that by dividing both of these by 2 and coming up with NH2. This would be considered the empirical formula for this compound. Now, this is not an actual compound, but it's representing that smallest whole number ratio of atoms to each other in a molecule. Down here, N2O, we cannot simplify that any further, so we would say this is both the molecular formula and the empirical formula. C6H12O6, which is sucrose or glucose. We see here that 6, 12, and 6, we can divide everything by 6. So we have 1, 2, 1. CH2O would be the empirical formula for this compound. H2O2, I can divide both of these by 2, right? This is hydrogen peroxide. It could simplify into just HO. Water, H2O. I have a 2 here. I have an imaginary 1. I cannot simplify that any further. So for water, this is both the empirical formula and the molecular formula. So how about looking at polar covalent bonding? What is a dipole moment? A dipole moment is simply representing a separation of charges. Why would that be? Well, fluorine really likes electrons, so it's going to pull the electron closer to it than what hydrogen can. So we say this is electron rich, which is why it's red in color. This is electron poor, which is why it is blue in color. This is an electrostatic potential map. So we can look then and basically assign that the fluorine atom is going to be slightly negative in this compound, and the hydrogen atom is going to be slightly positive. And we represent that by using the Greek symbol sigma and then a little negative sign, or sigma here and a positive sign, right? We don't put a charge of -1 on here because that would mean that fluorine completely took the electron. So it's only slightly negative because it's pulling the electron closer to it than what hydrogen is able to. Why would this be? Well, we have a term called electronegativity. And electronegativity looks at how strong of an attraction does an atom have to shared electrons. And these are arbitrary values that are assigned. It is not measurable, right? We talked about electron affinity in the last chapter, and that is the energy associated with an atom accepting an electron. Chlorine is the highest. However, of the electronegativity, right, they're all relative to each other. So there's lots of studies that have been done with these potential maps, seeing where are the electrons existing most of the time for different compounds. So electronegativity, fluorine is the highest. It has the strength to pull electrons towards it in a bond. So we have our periodic table that lists our electronegativities, and we can see that out of the periodic table, we are going to increase as we go across the row till we get to the halogens, and we decrease as we go down a column. And hopefully this makes sense, because we know that metals don't really want electrons, so they should have low electronegativities. Nonmetals would like to get electrons, so they have higher electronegativities. And here's another scale to just compare as we go across the row, starting with, starting with lithium going to fluorine. We see an increase in electronegativities. These are showing as we're going across the row. Notice we have our transition metals in the middle that do weird things, but we have a basic trend. We can also see here that with the exception of rubidium, we notice a decrease in electronegativity as we move down a column. So how can we use these electronegativities? Well, a classification of a bond type. So we can subtract the two numbers. We take two atoms, their electronegativities, subtract them to see what the difference is. If the difference is less than 0.5, we say that it's nonpolar, which means that the atoms are sharing those electrons equally. Nobody is pulling on the electrons any harder than their neighbor. When we see an electronegativity difference of 0.5, above 0.5, but less than 2, we say it's polar covalent. So this is where we end up in a situation of one of the atoms has the electrons floating around it more often than the other atom. When we see a difference of greater than 2, we classify that as ionic. And this is a sliding scale. So here we can look at a table and notice down here, where we're kind of in a non-polar region, we notice, right, chlorine, a Cl to Cl, they're sharing their electrons evenly. We have some other halogens, so these are all non-metals. Close to each other here, we see electronegativity difference of less than 0.5. As we go up and start bonding between metals and non-metals, we see that electronegativity difference get much greater. And we notice here, as we separate one end of the periodic table from the other, right? Lithium and fluorine. Lithium is in the beginning column of row 2. Fluorine is the second to last. So we see a large electronegativity difference, meaning that this is an ionic compound. But we have a sliding scale. We would expect lithium iodide to be ionic. Why? Because I've said if a metal shows up, it's got to be an ionic compound. But according to the difference scale here, we see that it's actually less than 2. So it's almost as if this is a polar covalent molecule. However, there truly is a transfer of electron from lithium to bromine, from lithium to iodine, etc. So we know that these compounds are truly ionic, which is why this scale is an arbitrary scale. For all intensive purposes, if you see a metal and a non-metal, it is ionic. It is an ionic compound. And what we're really concerning ourselves with then is what is happening when we have two non-metals bonded to each other. How do we classify that? Polar or non-polar. And the polarity of a molecule, right, that's just that dipole moment that exists, is something slightly positive, is something slightly negative. The polarity of compounds tells a lot about predicting certain physical properties like melting points, boiling points, if something is soluble in something else. So this is really important. So a molecule. Molecule, once again, is just a discrete unit of atoms that are sharing their electrons. When we have a diatomic, di means 2. So we have 2 atoms joined together. If we have a polyatomic, that means we have more than 2 atoms. And we've seen polyatomic ions. And those are all molecules, but they have a charge that exists overall on their structure. So here I have in blue the diatomic molecules. This means that when I say to you, hydrogen combusts in the presence of oxygen to form water. When I say hydrogen and oxygen in that sentence, that means that I have H2 and O2. And soon enough, we're going to have to start writing out balanced chemical equations to represent reactions. So you need to remember, you're going to have to memorize these, that if you say hydrogen, it's H2, nitrogen is N2, oxygen's O2, halogens, fluorine, chlorine, bromine, iodine, those are all diatomics, F2, Cl2, Br2, I2. They do not exist by themselves in nature. They are always together. So now that we know what a molecular compound is, we have to know how to name it. This is a different set of naming rules than what we see for ionic compounds. So the first element, whenever we write it, we just name it. Similar to ionic compounds. If carbon shows up first, we say carbon. If oxygen shows up first, we say oxygen. The second element takes an IDE ending. So this looks familiar as well. If the second element was sulfur, we'd say sulfide. If the second element's phosphorus, we say phosphide. Now, we always have to indicate the number of atoms by using prefixes. Because covalently bonded atoms are not charged, we don't have a true +2 or a true -3. We're not balancing charges. Molecules can bond in multiple different ways. You can take oxygen and nitrogen and form lots of different molecules, but you can only take lithium and fluorine and form one type of compound. So we have to use our prefixes to represent the number of those atoms in the compound. Now, when we have our first element, we never say mono in the front, but we say mono for the second atom if there's only one of them. For example, CO, carbon monoxide. Even though there's one C, we do not say monocarbon. But because of the second element, we have to say monoxide. Now, for the rest of the oxides, if you are using a prefix that has an A in it, we drop off the A, and so it would just be tetroxide instead of tetraoxide or pentoxide. So we don't say pentaoxide or hexaoxide. We just drop off the A, combine it. Now, similarly, we don't put two O's next to each other either. So we don't say monoxide or something like that. It's just monoxide, so no two O's together. However, we can have two I's next to each other because we can have diiodide or triiodide. And as always, there are common names for systematic names. So water, H2O, dihydrogen monoxide. Why? We have two hydrogens here. Di, one oxygen, mono, dihydrogen monoxide. Ammonia, right? It's a cleaning agent. Trihydrogen nitride, dry ice, carbon dioxide. Here we see salt, which is an ionic compound, sodium chloride, etc., etc. You do not have to memorize the systematic names for any of these compounds. Okay, so how do we actually draw structures for these covalent molecules? Well, we use what's called Lewis dot symbols and draw then a Lewis dot structure. The nice thing about the periodic table, once again, BFF, right? The PTOE is your BFF. When we look at our group numbers of our main elements, if you're a group 1, you have 1 electron in your outermost shell. Group 2 has 2. Look at the trend. Group 3 is 3, 4, 4, 5, 5, etc., etc. So your group number tells you your number of valence electrons. We also know this from writing out electron configurations. Highest energy level orbitals, whether it be S or an S and a P, that is where we count our valence electrons from. Carbon, using a noble gas configuration, would be helium, 2s2, 2p2. 2 plus 2 is 4, hence 4 little dots representing the valence electrons. So we're going to use these dot symbols in order to draw our structures. So how do we write out the Lewis structures? Well, we have to be given a chemical formula and identify which atom is going to go in the center. Usually the central atom, there's only one of them, and it's most often the least electronegative atom. So we have to have a total count of the number of electrons number of valence electrons present, and those all have to show up in the structure somehow, whether they are in a bond or represented as a lone pair. When we see a negative charge, for example, the carbonate ion, CO3, has a -2 charge. That means there are an extra 2 electrons. In NH4 plus of the ammonium ion, that plus means that we've removed an electron. So for every negative charge, we add electron. For every positive charge, we remove an electron. When we are going through here and we're making our bonds, there has to be at least a single bond between the central atom and all of the outside atoms. So when we're doing this and you're looking at your electron count, each bond that you make is taking 2 electrons away from your total valence electrons. Once you've made your single bonds, we place the remaining electrons on the outside atoms, or what they call terminal atoms, by placing those pairs of electrons. What the goal is to make sure that if you are an atom that needs to have 8 electrons to be stable, that you have your 8 electrons. Hydrogen will only, at a max, have 2 electrons. Why? Because it only has a 1s orbital, and that can only hold a max of 2 electrons. So any remaining electron pairs go on the central atom. And if when we go through and we do our count and there's not enough electrons on one of the atoms, for example, then we have to look at making multiple bonds. So making a double bond or making a triple bond. We will get lots of practice drawing structures in class. So nitrogen trifluoride, that means I have 1 nitrogen atom, 3 fluorines. Nitrogen is less negative, and it is also it's the lonely atom. So generally speaking, if we only have 1 atom in that structure, it goes in the middle. So we put nitrogen down and we draw some lines to look at connecting them. Here we have our total valence electron count. Nitrogen has 5, fluorine has 7, and since there are 3 fluorine atoms, we have to multiply that by 3. 5 plus 21 is 26 valence electrons. So we draw our single bonds, and then we start to add in the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we have 20 lone electrons here, not pairs, right? If it was pairs, I'd say I have 10 lone pairs of electrons. Then I can go and count to see, do each of my atoms have their octets filled? 2, 4, 6, 8 electrons for nitrogen, because every single bond represents a pair of electrons. I can look at each of the fluorine atoms and do the same counting. 2, 4, 6, 8, that one's good. 2, 4, 6, 8, that one's good. 2, 4, 6, 8, that one's good. Do I have my total number of electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons are represented here. 26 electrons were what we started with. So here's our structure for nitrogen trifluoride. Looking at another one, so carbonate ion. This is a polyatomic ion. Carbon is less electronegative than oxygen, so we put it in the center. How do we know it's less electronegative? We look at our periodic table. So carbon is surrounded by 3 oxygen atoms. How many total electrons? Carbon starts with 4, oxygen starts with 6, and since we have a -2 charge, we have to add in another 2 electrons. So we do our count. 3 oxygen atoms with 6 is 18, plus 2 is 20, plus 4. 24 valence electrons have to be represented in our structure. So we draw our single bonds between our atoms, then go in and add our valence electrons, and then we start to look at how many electrons does each have. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So are the number of electrons in the structure equal to the number of valence electrons? So now we go and we do our count to make sure that we have the total number of electrons we need. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there's a problem. We cannot have more electrons than what we're supposed to start with. So what do? There's too many electrons, so we have to form a double bond instead and then recheck our number of electrons. So I don't know why that circle's not showing up. So instead, we form a double bond between this carbon and this oxygen atom, and that allows us then to take these 2 electrons away from being on carbon, and our structure is complete. So some other examples of Lewis structures, when we have double bonding, that's going to represent that we have 2 shared pairs of electrons between the 2 atoms. So notice here, I've got 4 electrons between carbon and oxygen, 4 electrons here between carbon and oxygen, which means that I would draw 2 single lines between each of the carbons and oxygens. I can do an electron count, 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for carbon, 2, 4, 6, 8 for this oxygen. So those elements, carbon, nitrogen, oxygen, and fluorine, will always have to have 8 electrons. So we can also triple bond nitrogen, for example, right? This is a diatomic. I can share 3 pairs of electrons between the nitrogen atom, and simply represent that by 3 single lines here. This means 6 total electrons exist between the nitrogen atoms. Each nitrogen has 8 electrons, right? 2 plus 6 is 8, 2 plus 6 is 8. So we see that nitrogen forms a triple bond. Okay, so when there's a possibility of drawing more than one structure for a given formula, how do we figure out, excuse me, which structure is the better structure? Well, we have the calculation of formal charge, and that allows us to look at the number of valence electrons versus the associated electrons. So however many electrons you start with, right? For example, carbon starts with 4, hydrogen starts with 1, oxygen starts with 6. Then how many electrons are associated with it? Those are in bonds and lone pairs. So if there's a lone pair of electrons, we count 2 electrons for that atom. If it's a bond, then we only get half of those electrons. So for a single bond, each atom really only has 1 of those electrons. The important part here is that the sum of the formal charges of the atoms in a molecular ion must equal the charge on the overall molecular ion. So in the last slide, or the 2 slides ago, when we were looking at the carbonate ion, it has a -2 charge. That means that there have to be, excuse me, 2 atoms that each have a -1 charge, or there's 1 atom that has a -2, but somehow these charges have to add up and equal whatever the charge is that is represented on that molecule. Remember, if there isn't anything at the top right-hand corner of a molecule or a compound, it means that it is neutral. So the formaldehyde structure, right? Formaldehyde is used to preserve tissues, and it's embalming fluid. So here's one example. Carbon is 4 electrons, oxygen is 6. We have 2 hydrogens, each with 1 electron, total of 12 electrons. 2, 4, 6, 8, 10, 12. So we have all of the electrons represented. Now, looking at figuring out the formal charge on each of these atoms, I have 4 valence electrons for carbon. The number of electrons that are in bonds would be 1 here, 2, 3. Oh, sorry. This is total number of non-bonding electrons. 2 non-bonding electrons. Then we look at half of the number of bonding electrons. So I have 3 bonds. So I have 3 electrons that are coming from that carbon atom. Right? 1/2 times 6. So 4 minus 2 minus 3 gives me a -1. I can then calculate the formal charge on oxygen. Oxygen starts with 6 valence electrons. There are 2 electrons in the lone pair, non-bonding electrons. And then once again, I have 3 bonds coming from oxygen. So I have 3 electrons that are associated with oxygen, or 1/2 of 6 once again. So 6 minus 2 minus 3 gives me a +1 charge, which I would then write above the oxygen atom, because this is an actual charge. This isn't looking at polar covalent bonding where we just have that sigma saying this is slightly positive and this is slightly negative. These are actual charges that exist on these atoms. The other possibility for the formaldehyde structure, once again, 4 plus 6 plus 2 gives us our 12 valence electrons that have to show up in this structure. So I've got my 2 single bonds, which are 4 electrons. I've got a double bond here. That's another 4 electrons. And then I have 4 electrons in alone pairs for oxygen. So 12 is 12. I can look at calculating the formal charge again. On carbon, I'm starting with the number of valence electrons. I'm subtracting the number of any lone pairs of electrons, which carbon doesn't have any, and then looking at the number of electrons associated with it in a bond. So I can just count 1, 2, 3, 4 electrons, which is the same as saying 1/2 times 8. So 4 minus 0 minus 4 is 0. We do the same thing for oxygen. Starts with 6 valence electrons. I have 4 electrons associated that are non-bonding, right? These are lone pairs of electrons. Total number of electrons, 4. And then I look at the number of bonds that I have, which I have 2. I have a double bond here, which means there's a total of 4 electrons. But oxygen only has half of those, so 1/2 times 4 is 2. 6 minus 4 minus 2 is 0. So in this structure, I have carbon and oxygen both having a neutral charge. So which one of these structures is better? Well, when we have a neutral molecule, which formaldehyde is, the Lewis structure where there are no formal charges is preferable. So we're really in any structure, the more atoms that have a 0 charge on them, the more stable it is. Now, unstable structures would be when we have large formal charges. The difference between, say, having 2 atoms that each have a -1 charge on them versus a single atom that has a -2 charge on it. So it's better to have your charges distributed than having a large charge, whether it be negative or positive, on a single atom. Now, when we have the option of placing a negative charge on different atoms in a structure or a positive charge on different atoms in a structure, the more electronegative element is going to be more comfortable with the negative charge. So we look to our periodic table and compare our electronegativities. For example, a structure that has nitrogen and oxygen in it, if need be, the oxygen would want to have the negative charge because it is more electronegative. We can also say that something is more electropositive, which just means that it would rather have the positive charge. So when placing formal charges, we need to think about what charge is and what type of atom is it on. Is it on the more electronegative atom? We don't want a positive charge on the more electronegative atom. So when we looked at the first structure here, we have a -1 on carbon. We have a +1 on oxygen. This is not good. Oxygen is more electronegative than carbon, so these 2 charges are not where they should be, but this is what it is. Here, I've got 2 charges of 0. This is a much more stable structure. It's a neutral molecule. We should have neutral charges. But notice, -1 + 1 adds up to 0. So this is an acceptable structure for formaldehyde. It's just not the correct structure. So when we have polyatomic ions, most often, there's also this example here. This first example is ozone, which is an O3 molecule. It is neutral. And we notice here the central oxygen in both of these structures has a positive charge. And one of the outside oxygen atoms has the negative charge. So resonance structure is when we can take a molecule and place lone pairs of electrons or double bonds in different places. And we'll learn later, these are called pi electrons. So you're allowed to move your pi electrons around. I am not allowed to draw a resonance structure in which the basic connectivity of those atoms is changing. It's no longer resonance then. You're changing the structure completely. It's not the same thing. So from this structure to this structure, what has happened? A pair of electrons here has now decided to bond between these 2 oxygen atoms, which then kicks these electrons back to this oxygen atom. I cannot break any octet rule. I cannot have double bonds on both sides and then have this lone pair of electrons on oxygen. Why? Because that would give oxygen 10 electrons, and that is not allowed. Carbon, nitrogen, oxygen, fluorine are the 4 atoms which, no matter what structure they show up in, they have to have 8 electrons. They cannot have any more. So resonance really is just looking at where can I place my extra electrons? Can they be in a double bond? Are they going to be on a different atom? These are both acceptable structures of ozone, and neither one of these is more stable than the other because I have the same types and number of charges on similar atoms. And resonance, there isn't really ozone that just exists like this and just exists like this. What we really see, if we looked at an electrostatic potential map, is that there's a general sharing of these extra electrons across these bonds. So we would see that it's not a true double bond. And we can measure bond lengths and bond energies, and it proves this theory in that the distance between these two oxygen atoms is not truly representative of what a double bond would be, nor do we see the distance of a single bonded oxygen. It's almost like we're in the middle of a bond and a half. So we can also look at the resonance structures for the carbonate ion. And once again, I'm only allowed to move double bonds and lone pairs of electrons. So I can draw another structure where my double bond is in a different place. And if I take this double bond and I move it somewhere else, then I'm going to have to take an extra pair of electrons and put it back onto this oxygen atom. So if we push the double bond up here, that basically means that the extra electrons that were here now go down here. Why? Because I have to follow the octet rule. 8 is great. 2, 4, 6, 8, 2, 4, 6, 8. Not changing the number of electrons that are associated with these atoms. Just how they are associated. So I had the double bond here to start. I have the double bond here. And guess what? I could also have the double bond here. And then this atom goes back to having an extra pair of electrons. These are all resonance structures of each other. Not one of these truly exists in nature. But what we see once again is a general sharing of extra electrons along all of these bonds. So we do not see a true single bond or any true double bonds between the carbons and the oxygens. And as always, there are exceptions to the octet. As I talked earlier, hydrogen can only have 2. Beryllium would also only have a max of 4 electrons around it, and this is because beryllium is it has that s electron, or has that s orbital. That's where they can go. It can't have any more. Sorry, not 4 electrons. 2 electrons are associated. Yes, it's 4. I can count. There's 2 here with this hydrogen. There's 2 here with this hydrogen. So beryllium then has a total of 4 electrons. How about boron trifluoride? This is considered an incomplete octet as well, not being able to have 8 electrons. Boron starts with 3, fluorine starts with 7. I have 3 fluorines, so 3 times 7, 21. 3 plus 21 gives me a total of 24 electrons. Boron trifluoride. Boron shares its 3 electrons with fluorine. The fluorines have their stability, 8 around here, 8 around here, 8 around here. However, boron only has a total of 6 electrons, 2 from each bond that is associated with this. This allows boron then to do some special chemistry where it can actually accept another pair of electrons. So boron is an example of an incomplete octet, as is beryllium. We can also have the option of odd electron molecules. NO, right, it's a gas. We only have 11 electrons. So I have 2, 4, 6, 8 here. Unfortunately, nitrogen does not have its 8. 2, 4, 6, 7. Now, why would we have the extra electron on oxygen and not on nitrogen? That is because oxygen has a higher electronegativity. This is not a stable molecule. This is something we call a radical. When we only have a single electron, these are very reactive. And if you hear in the news or you read about free radicals and wanting to have antioxidants, this is why when you eat, say, blueberries and they're high in antioxidants, a molecule like this then reacts with those compounds in there instead of attacking your molecules that you actually really need in your body. So free radicals can be combated with antioxidants. because essentially this nitrogen is really going to want to find another electron, and it'll try and take it from somewhere else. The last example is what we call an expanded octet. So this is when we have more than 8 electrons. And it says here that our central atom has to have a principal quantum number of greater than 2. So we're looking at our third row and below. And that is because those nonmetals have empty d orbitals, right? We don't have enough electrons to put in those d orbitals yet, but when n equals 3, I can have L be 2, 1, or 0, which means D, P, and an S. So it's like we go back to that idea of orbitals being like pockets. If you've got an empty pocket, you can put your electrons in it. So for example, sulfur hexafluoride, hexa because there's 6. Sulfur is going to be my central atom. 6 electrons here, 7 for each of the fluorines. 7 times 6 is 42. Added up, I should have a total of 48 electrons. And I do indeed. Sulfur is actually 2, 4, 6, 8, 10, 12 electrons around it. This is acceptable because sulfur has that empty d orbital. Notice each of my fluorine atoms has 8 electrons around it because it has to have 8. So this is an acceptable structure because sulfur can have an expanded octet. And if you want to, I suggest that you do count all these electrons to make sure that they are all there. So in this chapter, we need to learn how to name our molecules. And please keep this separate. We can only use prefixes when we have 2 nonmetals coming together. If there is a metal, we never have a prefix associated with it. And then really the second part of this chapter is dealing with drawing structure. So we are going to draw a lot of structures. You need to get practice with this, because then once we draw our structure, we can figure out, is it polar? Is it nonpolar? We can look at, is there a possibility of drawing a resonance structure? And if there is, what are the formal charges? Which of those structures would be the most stable out of the ones that we drew? And then leading into the next chapter, we're going to be able to assign shapes to these molecules. So we have to know how to draw a Lewis structure in order to assign the shape. And then we can actually discuss whether or not overall this molecule is polar or nonpolar, right? At this point, we can only say whether the bonds themselves are polar or nonpolar. So good luck studying, and I will see you all soon.